Hello everyone, welcome to the second part of tutorial 9. So, let us start with question number 7. So, here we first define what we call as the degree sequence of a graph, and the degree sequence of a graph is basically the sequence of degrees of the vertices in non increasing order. So, you list down the highest degree vertex or the degree of the highest vertex first, followed by the next highest degree, followed by the next highest degree, and so on. So, if you have n vertices, basically you are listing down the degrees of the n vertices in a non increasing order. And we say a sequence of n values is a graphic sequence if you can construct a simple graph whose degree sequence is the given sequence. Okay. If you can't draw any simple graph whose degree sequence is a given sequence, then the given sequence will not be called as a graphic sequence. So, I stress here that we need the graph only to be simple, it need not be connected, it need not be connected. Okay. It is fine if the graph is not connected. Okay. So, the first few parts of question 7 basically ask you to prove or disprove which of the given sequences is a graphic sequence. So, let us take the first sequence 5 4 3 2 1 0. Of course, one obvious condition in a graphic sequence should be that the values should be non-negative. You can't have a vertex with a negative degree. Okay. So, that is a trivial condition. So, in this case we have to verify whether we can draw a simple graph with 6 nodes where the highest degree is 5 and the smallest degree is 0, and it is easy to see that this sequence is not a graphic sequence, because you can't draw a graph with 6 nodes you can't draw a simple graph with 6 nodes where the maximum degree is 5 and the minimum degree is 0. Okay. Because if say V1 is the vertex which has the maximum degree, so if its degree is 5, then it should be a neighbor of each of the remaining 5 nodes. Okay. That means each of the remaining 5 nodes will have a degree which is non-zero, but you also need a vertex with a degree 0 among those 6 nodes, which is not simultaneously possible. Okay. So, now let us take the second sequence and try to argue whether this sequence is a graphic sequence or not, and again this sequence is not a graphic sequence. There are several ways you can refute, but there are several ways by which you can refute that this sequence is not a graphic sequence. One simple way is that if you take the sum of the values that are given in this sequence is not an even quantity, but we know that for any graph it need not be a simple graph. For any graph, the sum of the degrees of all the vertices is twice the number of edges, which is an even quantity. So, one obvious condition that should be satisfied by any graphic sequence is that if you sum the values given in the sequence, it should be an even quantity, which is not the case for the sequence given here. Now, let us consider the third sequence, and this sequence is a graphic sequence, and this is a simple graph which realizes or which has this degree sequence. Okay. So, now in question 8 we want to characterize that, we want to find out a characterization for graphic sequences, right. So, if you are given a sequence with n values, how can you verify whether that sequence is a graphic sequence or not, right. We can't keep on drawing all possible simple graphs and then either prove or refute that the given sequence is not a graphic sequence. We need an algorithmic characterization, a necessary and sufficient condition, and that is given by what we call as Havel-Hakimi theorem. So, here you are given the following: you are given a sequence S of n non-negative integers in non-increasing order, and you have a reduced sequence S star. It is reduced in the sense it has n minus 1 values, okay, whereas the sequence S has n values. So, how exactly we construct a sequence S star? So, the way we construct S star from S is the following: we first remove the value d1, and then from the next d1 degrees or from the next d1 values in the sequence S, we subtract 1 from each of those d1 values in the sequences. So, d2 gets decremented by 1, d3 gets decremented by 1 and d1 plus 1th term gets decremented by 1, whereas from d1 plus 2th term to the dnth term the degrees remain the same as they were in the sequences. So, that is the way we obtain the sequence S star. And what Havel-Hakimi theorem says is the following. It says that your sequence S is a graphic sequence if and only if the reduced sequence S star when arranged in a non-increasing order is also a graphic sequence. Okay. So, for the moment imagine that this theorem is true. How exactly we can use this theorem to verify whether a given sequence of S values is a graphic sequence or not? Well, we have to reduce the sequence S and build a new sequence S star and then rearrange the terms in S star so that the new degrees are in non-increasing order. And now we have to verify whether the reduced sequence S star is a graphic sequence or not. To do that I can again apply the Havel-Hakimi theorem. Now this reduced sequence S star can be further reduced to n minus 2 degrees, where I can remove the first degree from S star, and to compensate that I subtract 1 from the next few degrees, and then the next reduced sequence again is arranged in a non-increasing order, and then we can verify whether that sequence is a graphic sequence or not. And I can keep on repeating this process, keep on decreasing my sequence till I obtain a very short sequence which I can very easily verify whether it is a graphic sequence or not. If it is a graphic sequence, then I can come back all the way and declare that my big sequence, my original sequence is a graphic sequence. Whereas, if the reduced sequence or the small sequence at which I stop and inspect and find out that it is not a graphic sequence, then I can declare that my original sequence is also not a graphic sequence. So, that is the way I can apply the Havel-Hakimi theorem to verify whether a given sequence is a graphic sequence or not. So, now let us prove this theorem, and this is an if and only if statement. So, we have to prove two implications. Let us first prove the easier one. So, we want to prove that if S star when arranged in a non-increasing order is graphic, then so is the sequence S. What does mean? That so I will give a direct proof for this implication. And when I say I will give a direct proof, I mean to say that I will assume that my premise is true and I will arrive that my conclusion is also true. So, assume that my premise is true. That means, since my sequence S star is a graphic sequence, I can construct a graph, a simple graph G star with n minus 1 vertices and some edges whose degree sequence is the same as the sequence S star. What does that mean? So, I can imagine that my vertex set V star has n minus 1 nodes. I call those nodes as V2, V3, Vn, and since it realizes the sequence S star, that means I have a vertex of degree d2 minus 1. Let V2 be that vertex. I will have a vertex with degree d3 minus 1. Let V3 be that vertex, and like that I will have a vertex of degree this much. Let V of d plus 1 be the vertex with that much degree, and like that I will have a vertex of degree dn, and let V of n be the vertex with that degree. Okay. That is the implication of assuming my premise to be true. Now, and my graph G star is a simple graph, remember. Apart from that, I do not know anything about G star, whether it is connected or not connected and so on. Now, from G star I have to build another graph G which has n nodes, which is simple and whose degree sequence is the same as the sequence S. That is what is the implication. Okay. So, the construction of the graph G is very simple. I take a copy of G star as it is, and since I have to give a graph which has n nodes, but since I have taken the graph G star, I have currently n minus 1 node. So, what I will do is I will now include a new node, call it V1, and I have to give some edges to this vertex V1. So, what I do is I add the edge between the vertex V 1 and the vertex V 2 which has earlier degree d 2 minus 1. I add an edge between the vertex V 1 and the vertex V 3 which has which had earlier the degree d 3 minus 1, and similarly I add the edge between the vertex V 1 and the vertex number d 1 plus 1 which had earlier the degree d 1 plus 1. Okay. Okay. And the remaining edges they remain as it is in the graph G. Now, what can I say about the new vertex of the degree V 2? What can I say about the degree of the what can I say about the new degree for the vertex V 2? It will be 1 more than it was earlier. So, earlier the degree was d 2 minus 1, but now since I have given a new edge to the node V 2, its degree will now become d 2. Similarly, the new degree of the vertex V 3 will become 1 more than it was earlier. So, it will become d 3, and like that degree of the d plus 1th vertex will be 1 more than what it was earlier. So, it will become this much, and the degrees of the remaining vertices will remain as it was earlier. And what can I say about the degree of the vertex V 1? It will be d 1, because I have added d 1 edges incident with the vertex V 1. And now you can see that this sequence is nothing but the sequence S. That means, in the sequence S you need to have one vertex of degree d 1. So, I have one such vertex, namely V 1. You need to have a vertex of degree d 2, I have one such vertex, namely V 2. You need to have a vertex of degree d n, I have one such vertex, namely V n. So, I have now a simple graph whose degree sequence is same as the sequence S. So, that shows that this implication is true. Now, let us prove the implication in the reverse direction. So, I want to prove that if your sequence S is graphic, then the reduced sequence S star when arranged in a non increasing order is also graphic. Okay. And again I will give a direct proof. That means, I will assume that my premise is true and I will arrive at my conclusion. So, since my premise is true, that means I have a simple graph, call it G with n nodes and some edges whose degree sequence is same as the sequence S. That means, you have n vertices, say V 1 to V n, and let V 1 be the vertex which has degree d 1, V 2 be the vertex which has degree d 2, V n be the vertex which has the degree d n. Okay. Now, from this graph I have to arrive at another graph which is simple with n minus 1 nodes and which realizes the sequence S star, the reduced sequence S star. So, how do I do that? So, I will use now a proof by cases. So, once I assume my premise to be true, I will do a proof by cases, because there will be two cases which will be happening depending upon what exactly is the structure of the graph G. So, your case 1 will be the following. Imagine your simple graph G is such that the vertex V 1 which has degree d 1 is adjacent to the vertex which has degree d 2, it is adjacent to the vertex which has degree d 3, it is adjacent to the vertex V 4 which has degree d 4, and like that it is adjacent to the vertex which has degree d 1 plus 1. Suppose that is the case. Okay. Case 2 will be when this is not the case, right. So, case 1 is when V 1 is adjacent to the vertex which has degree d 2, it is adjacent to the vertex V 3 which has degree d 3, and it is adjacent to the vertex which has degree d 1 plus 1. Now, let us see what will happen if I delete this vertex V 1 and the edges which are incident with the vertex V 1, because if I delete the vertex V 1, of course, these edges will no longer be there. Okay. So, I will obtain now a new graph G star, which will be of course simple, because my original graph G was simple. So, I am not adding any edges, I am deleting edges. So, by deleting edges I will still obtain a simple graph. So, my graph G star will be a simple graph and it will have n minus 1 nodes, because I am reducing one vertex, namely V 1. Now, what can I say about the new degrees of V 2, V 3 and the vertex number D 1 plus 1? Well, the degree of V 2 will be 1 less than what it was earlier, because the edge between V 2 and V 1 has vanished. The degree of V 3 will be 1 less than what it was earlier, because the edge between V 3 and V 1 has vanished, and the degree of the D plus 1th vertex will be 1 less than what it was earlier, because the edge between the D plus 1th vertex and vertex number V 1 has vanished. The degrees of the remaining vertices will remain as it was in the graph G. So, now what can you say about this sequence? I can say that this sequence is nothing but the sequence S star in non increasing order. Namely, I can say that there is a graph, simple graph, namely G star, which realizes the sequence S star, because in S star, in order that S star is a graphic sequence, you need a vertex of degree D 2 minus 1 in G star, and you have one such vertex, namely V 2. You need one vertex of degree D 3 minus 1 in G star, and you have one such vertex, namely V 3, and you need one vertex of degree this much, and you have a vertex in G star with that much degree. You need a vertex of degree D n in G star, and you have a vertex whose degree is D n. So, that means now I can say that G star can realize the sequence H star, and hence my sequence H star is also graphic. So, that is case 1. Now, case 2 will be the following. Case 2 is the case 2 case 2 occurs where in the graph G, which realizes your sequence S, the structure is as follows. There is at least one vertex V I in the set V 2 to the D plus 1th vertex, such that V 1 is not adjacent to that vertex. So, what do I mean to say here is the following. In case 1, if you see, the situation was that V 1 was adjacent. So, V 1's degree was D 1, and those D 1 edges were contributed from the next D 1 vertices, namely the next vertices who D 1 vertices which has the degree D 2, D 3, D 4 and D 1 plus 1. Okay, that was case 1. In case 2, we are considering the case where this is not happening. That means, you have at least one vertex V I outside this set V 2 to D 1 plus 1 vertex number D 1 plus 1, such that V 1 is not adjacent to V I. So, what do I mean by that? For instance, imagine that your D 1 is equal to say 4. In case 1, what was happening is the following. You need V 1 to have 4 edges incident with V 1. That means, 4 edges should be incident with V 1, that is why its degree was 4. So, those 4 edges were between V 1 and V 2, where the degree of V 2 was D 2. It was between V 1 and V 3, where the degree of V 3 was D 3. It was between V 1 and V 4, where the degree of V 4 is D 4, and it was between V 4 and V 5, where the degree of V 5 is D 5, and of course, the degrees are now in non increasing order. That was happening in case 1, but in case 2, what is happening is your degree D 1 is still 4, but either the edge between V 1 and V 2 is missing, or the edge between V 1 and V 3 is missing, or the edge between V 1 and V 4 is missing, or the edge between V 1 and V 5 is missing, where V 2, V 3, V 4 and V 5 are the vertices with degree D 2, D 3, D 4 and D 5 in the graph G respectively. Okay. So, now I can't run the same argument which I used in case 1. In case 1, I simply deleted V 1, due to which all these edges which were there between V 1 and vertex 2, vertex 3, vertex 4, vertex 5, they vanished, and the degrees of d 2, d 3, d 4, d 5 automatically got decremented by 1. I can't run the same argument here, because say for instance, if the edge between V 1 and V 2 is missing, then by deleting V 1 I can't say that the degree of V 2 gets decremented to d 2 minus 1, because V 2 is not adjacent to V 1, its degree will remain the same, namely d 2. Or say for instance, the edge between V 1 and V 3 is not there, then deleting V 1 will only it will not change the degree of vertex V 3, it will still remain d 3 and so on. So, I can't run the same argument which I easily or conveniently used for case number 1. So, I have to do something more to handle the case number 2. And by the way, these are the only two cases, either case 1 could occur or case 2 could occur, there can't be any third case possible. So, the proof strategy here will be the following. What I will do is, I will do some transformation, and we will see how exactly the transformation happens. We will do some transformation on the graph G and convert it into another simple graph H with n vertices and with the same degree sequences. That is important. That means, whatever were the characteristics of G, they remain the same. So, G was simple, the transformed graph H also will be simple. G had n nodes, the transformed graph H also will have n nodes. The number of edges in G will be the same as the number of edges in H, and G was simple, H will be simple. G realized the degree sequences, and the transformed graph H also will realize the same degree sequences, but H will now have a characteristic which was not there in the graph G. So, in the graph G there was some node V I in this set. Okay. So, let me call this set S F. So, there was some node V I in the set F such that V 1 was not adjacent to that node V I. But after transformation, what we will do is, we will ensure that V 1 is adjacent to each node in the set F. That means, the degree d 1 which is attributed to the vertex V 1 is coming because of the edges between the vertex V 1 V 2, vertex V 1 V 3, vertex V 1 V 4, vertex V 1 and d plus 1th vertex. That means, what I can say now is that my transformed graph H is exactly having the same structure as we had for the graph G in case 1. And now I can apply the same argument that we used for case H, case 1. So, now I will say that okay, I will forget about the graph G, I will say that okay, now I have a graph H which is simple, which has n nodes and which realizes the degree sequence S, and where the degree where the vertex with the highest degree d 1 is adjacent to the next immediate d 1 vertices. So, I can remove the vertex V 1 and argue that because of the removal of the vertex V 1, the degree of the next d 1 vertexes will get decremented by 1, and that will be an instantiation or realization for the sequence S star. So, that is a proof idea. So, now everything boils down to how exactly we do the transformation. So, the transformation is as follows. So, remember, the structure in the graph G is the following. There is at least one node V I in the set F such that the edge between V 1 and V I is missing. And I also know that since the degree of the vertex V 1 is d 1 and the edge between V 1 and V I is missing. So, to compensate this missing edge, namely to ensure that the vertex V 1 has the degree d 1, there must be some outside vertex. And what do I mean by outside vertex? Namely, that vertex is not in the set F, but in the remaining n minus d 1 vertices. Okay. It is not among the first d 1 vertices. So, this vertex V j is the outside vertex, and there must be an edge between V 1 and that outside vertex V j, because we have to take care of the fact that the degree of V 1 is d 1. So, again for instance, what I am saying here is if d 1 is 4. So, in case 2 we know that either the edge between V 1 and V 2 is missing, or the edge V 1 V 3 is missing, or the edge V 1 V 4 is missing, or the edge V1 V5 is missing. But since I have to give degree 4 to the vertex V1, that means V1 is adjacent to either vertex 6 or vertex 7 or vertex 8 and so on. So, that is the vertex Vj, that is the outside vertex Vj in my current context. And what I know is that in my graph G, the vertex Vi, its degree Di is as large as the degree of the vertex Vj, okay, because that is the structure of my graph G. So, that means there must be some neighbor of Vi, call it Vk, which is not a neighbor of Vj, because if every neighbor of Vi is also a neighbor of Vj, and on top of that Vj is a neighbor of V1, but Vi is not a neighbor of V1, we arrive at the conclusion that the degree Dj is more than the degree Di, which is not the case, right. So, that is a very simple proof of the fact that there must be some neighbor, namely Vk, which is there must be some neighbor Vk of Vi, which is not a neighbor of Vj. Okay. So, that is the structure present in your graph. Now, what the transformation does is the following: since the edge between V1 and Vi is missing in G, but after transformation I want that edge to be present. So, I add that edge, but that will increment the degree Vi or degree of Vi. I do not want to do that. So, to compensate this new edge which I have given to Vi, I take away the edge which was earlier present between Vi and Vk. Okay. So, that ensures that the degree of Vi remains the same, and I have to take away the edge between V1 and Vj, because since I am giving a new edge to V1, the degree of V1 will get incremented, which I do not want to do. So, to compensate that, I take away the edge between V1 and Vj which was earlier there, but that will reduce the degree of Vj again, which I do not want to do, and to compensate that I add the edge between Vj and Vk. And this whole process I am not disturbing the property that my graph G or the transformed graph H is a simple graph. So, my transformed graph H still remains a simple graph, but by doing this transformation what I have done is the following: earlier this vertex Vi was not immediately a neighbor of V1, but now in my transformed graph Vi is a neighbor of V1. So, I can repeatedly apply this transformation for all the outside vertices Vi, and after doing the required number of transformation I will get my graph H, which will have the same structure as in case 1, and then the proof becomes the same as it was in the case 1. So, that proves the implication in the other direction. In question number 9, we want to either prove or disprove whether this sequence is a graphic sequence. So, there are two options: we can use either Havel-Hakimi theorem, or we can use a proof by induction to prove that this sequence is a graphic sequence, but we will give a constructive proof to show that the sequence is graphic by showing a graph, a simple graph with 2n nodes whose degree sequence is same as S. So, here are the vertices, 2n vertices, and what I do is the following: I take the vertex V1 and add the edge with all vertices with even indices. I take the vertex V3 and I add an edge with all even index vertices except the vertex V2, and I keep on doing this process, and for the last vertex with odd index I will give only one edge, namely an edge with the last vertex with even index. Now, what I can say about the degrees of the respective vertices here? So, it is easy to see that these two vertices will have degree n. So, indeed I need two vertices of degree n. I will have this vertex of degree n minus 1 and this vertex of degree 2. So, I got one vertex of degree n minus 1 and one vertex of degree 2, and if I continue I will find that I will get two vertices of degree 1, and then eventually I will obtain the second vertex of degree n minus 1 and so on. Okay. So, the vertex here will be of degree n minus 1 and so on. So, that is a very simple construction to show that this sequence is a graphic sequence. Now, let us come to question number 10. Here we want to prove that if you are given a graph with n vertices and if you are doing edge coloring, then you can't use a single color to color more than n by 2 edges, and it is a very simple fact. Depending upon whether your n is odd or even, we can prove this very easily. So, let us take the case where n is even. So, remember each edge has 2 endpoints. That means, if I consider n by 2 distinct edges of the graph, and if I focus on their endpoints, that will constitute the entire vertex set, right. So, that means I can't color n by 2 plus 1 edges with the same color, because if I do that, then their endpoints will give me n plus 2 vertices, but my graph at the first place has only n vertices. So, at most I can use n by at most I can color n by 2 edges, distinct edges with the same color. I can't color more than those many edges, whereas if n is odd, then this quantity n by 2 is not well defined, it will not be an integer value. So, n by 2 in the context of an odd value of n will be n minus 1 over 2, and indeed it is easy to see that I can't use a single color to color more than n minus 1 over 2 number of distinct edges, because if I try to do that, say for instance I try to color n by n minus 1 over 2 plus 1 number of distinct edges, then their endpoints will give or constitute will n plus 1 nodes, but at my my given graph has only n nodes. So, that is a maximum number of edges, distinct edges, which can be colored with a single color. Now, based on these information, I will try to solve question 11, where I want to find the edge chromatic number of a complete graph with n nodes, and my solution will be divided into 2 cases depending upon whether my n is odd or even. So, remember from the previous question, I know that if your n is even, then you can use one color and color at most n by 2 edges. Whether indeed you will be able to color n by 2 edges or not, that depends upon the structure of your graph, but at max you can color n by 2 edges using a single color. Now, in a complete graph k n, I have n into n minus 1 over 2 number of edges. So, with color number 1 I can take care of at most n by 2 edges. With color number 2 I can take care of another set of n by 2 edges. So, like that, how many colors I will require at least? So, I will require at least n minus 1 number of colors, because through the first color I can take care of n by 2 edges, through the next color I can take care of another bunch of n by 2 edges, and I have to take care of n minus 1 such bunches of n by 2 edges. So, that is why the minimum number of colors that will be required will be n minus 1. Whereas, if I take the case when n is odd, then from my analysis of question 10, I know that through one color I can take care of at most n minus 1 over 2 number of edges, and I have to take care of n bunches of n minus 1 over 2 number of edges. So, that means I will require at least n colors if my n is odd. Now, what I will show is, I will show that these bounds on the edge chromatic numbers, which were the lower bounds, because they were the least number of colors which were required, they are actually tight. In the sense, I will give you a constructive coloring, a concrete coloring for coloring the edges of a complete graph with n nodes where n is even, and where the number of colors required is exactly n minus 1. And you can't beat this bound, because the lower bound says you will need at least n minus 1 colors. So, that is why I am giving you an optimal coloring. So, let me demonstrate the coloring assuming the value of n is equal to 8. So, remember edge coloring here corresponds to scheduling of a round robin tournament. So, we have 8 teams and we have to schedule matches among the teams, and the requirement is that each team has to play against every other team once, but at the same time we do not want to enforce a team to play more than a single match on any day. So, the way I do the coloring here is as follows. So, on the first day I keep V8 at center and engage V8 with V1 and engage V2 with 7, engage V3 with 6, engage V4 with 5. So, this is equivalent to saying that this color C1 is used to color the edges between V4, V5, V3, V6, V2, V7 and V1, V8. right. That means, I have colored the maximum number of edges using color number 1, and now I have to use color number 2, and using color number 2 I will try to color another set of 4 edges. So, how do I, which is equivalent to saying that I now want to find a schedule for the next day. So, the schedule for the next day is obtained by kind of rotating this diagram by 30 degrees and changing the assignment of or engagement of V8. So, earlier V8 was engaged with V1, but now V8 will be engaged with the next team in the clockwise direction, which is V2. So, now the assignment of the colors is the following. So, I use the color number C2 to color these 4 edges, or equivalently I schedule these matches on day number 2. Then again I shift it by 30 degree and change the engagement of V8. Now, V8 will be engaged with V3 and so on. So, now you can see that I have to do this rotation 7 number of times, and then I will be able to color all the remaining all the edges of my complete graph with n nodes, 8 nodes. Okay. Now, let us see how exactly we can color all the edges of a complete graph with n nodes where n is odd, and I will be using exactly n colors, which is optimal, because the lower bound says that for n being odd I need at least n colors. So, the idea here is I can convert the complete graph with n nodes to a complete graph with n plus 1 nodes by adding a new vertex and the required dummy edges, and since n was odd, n plus 1 will be even, and I know a coloring mechanism to color a complete graph with n plus 1 nodes where n plus 1 is even using n colors, namely the coloring that I had discussed just now. So, take that coloring and now you delete the dummy node and the corresponding edges, that will give you the coloring for the original complete graph with n nodes where n was odd. So, for instance, what I am saying here is if you have only 7 teams and you want to come up with a schedule, you imagine that you have included a dummy team, say the 8th team, and now you want to come up with a round robin schedule tournament for 8 teams with the same restrictions that you had earlier. So, this will be the schedule, you will require 7 days. Now, in the first day you can see that on the first day you can see that V8 is engaged with V1. So, you can forget about that, you can imagine that that match is not going to be held. Remaining other matches will be held as per the coloring assignment, namely V2 will play with V7, V3 will play with V6 and V4 will play with V5. In the on the second day V8 is engaged with V2. So, you can imagine that that match will not be there actually, and remaining 3 matches will be played and so on. So, this now gives you a coloring edge coloring for complete graph with n nodes when n is odd. Okay. Fine. Now, question 12, we are giving a greedy strategy for vertex coloring, and we want to prove that this strategy need not give you the optimal vertex coloring. So, the coloring strategy is the following. We first sort the vertices according to their degrees and then use color number 1 to color the vertex which has the highest degree that you have arranged as per your degrees, and then the next degree which is not adjacent to and the next vertex in the list which is not adjacent to V1 if at all it exists, and successively try to color as many vertices as possible according to the color number 1, keeping in mind that the next vertex which you are selecting is selected according to their degree. That means, you are following a greedy strategy and trying to occupy or color as many vertices with that color, and now do the same process with the next color and so on. So, now we have to give a counter example, namely a graph where Welch-Powell algorithm will end up utilizing more color than the optimal number of colors. So, consider this graph and let us see how many colors we need. So, actually we need 4 color as per the Welch-Powell algorithm, because this vertex has the highest degree. So, I will color it and then I can assign the same color to this vertex which has also the same degree, and now I can't use the same color to color any other vertex. Now, I will focus on the next set of vertices which has the highest degrees. So, let us use this vertex, and then the same color I can assign to this vertex and this vertex. So, that is the maximum number of vertices which I can color with the second color. Now, among the remaining vertices I will pick the vertices which have according to their degrees. So, I can pick this vertex and the same color can be assigned to this vertex. Okay. So, we need total 3 colors here, but the optimal coloring is 2. It means it will require only 2 colors and 2 colors will be sufficient to color all the vertices in this graph. So, that shows this is not optimal coloring. Okay. So, with that I conclude this tutorial. Thank you.